Isolating the ground on a 20-amp receptacle provides several benefits, primarily improves safety. Isolating the ground prevents current from flowing through the ground wire, thereby reducing the risk of electric shock. In the event of a ground fault, such as a damaged appliance, isolating the ground prevents the fault current from tripping nearby circuits, ensuring uninterrupted power to essential loads. Secondly, it helps with code compliance. In certain applications, like isolated ground circuits in healthcare facilities, isolating the ground is required by electrical codes for patient safety. Floating the ground on a 20-amp receptacle can help meet these isolated ground circuit requirements. Thirdly, it aids in reducing noise and interference. Ground loops can cause noise and interference in audio and video systems. Isolating the ground breaks the ground loop, reducing these problems. It can also minimize electromagnetic interference from appliances or electronic devices. There are other benefits. Isolating the ground frees up one wire in the conduit, allowing for an additional hot or neutral wire, thereby increasing the circuit's power capacity. Reducing ground currents and minimizing electromagnetic interference can extend the lifespan of electrical devices and wiring. Isolating the ground on a 20-amp receptacle allows for easy troubleshooting of ground faults without disrupting other circuits. Examining safety aspects further, a properly grounded electrical system is designed to provide a low impedance path for fault currents to return to the source. This low impedance path facilitates the quick tripping of a circuit breaker or blowing of a fuse, thereby disconnecting the faulty circuit and minimizing the risk of electrical shock or fire. However, in some sensitive electronic equipment, the presence of ground loops can introduce noise and interference that can degrade performance. An isolated ground system, on the other hand, provides a dedicated grounding path that is separate from the normal equipment grounding conductor. This dedicated path minimizes the flow of stray currents, reducing noise and interference, and providing a cleaner, more stable ground reference for sensitive electronic equipment. This is especially important in environments where precise and accurate measurements are critical, such as in hospitals or research laboratories. Compliance with electrical codes is paramount to ensure the safety and reliability of electrical installations. The National Electrical Code, or NEC, provides detailed guidelines and requirements for grounding and bonding electrical systems. Article 250.146 covers the requirements for connecting the grounded conductor to grounding electrodes. Depending on the specific application, isolated ground systems may be required to comply with specific provisions of the NEC, such as Section 517.16, which addresses healthcare facilities. Isolated ground systems are commonly employed in data centers, recording studios, and other environments where noise and interference can be detrimental to the operation of electronic equipment. By providing a dedicated grounding path, isolated ground systems minimize the flow of stray currents and provide a cleaner, more stable ground reference, resulting in improved performance and reliability of sensitive electronic equipment. Ground loops arise when there are multiple ground paths between two or more pieces of equipment. These multiple paths create a loop in which stray currents can circulate, introducing noise and interference into the electrical system. Isolating the ground eliminates one of these ground paths, breaking the loop and reducing the flow of stray currents. This is particularly beneficial in audio and video systems, where even small amounts of noise can significantly degrade the quality of the signal. Electromagnetic interference, or EMI, is a type of disturbance that can affect the performance of electronic equipment. EMI can be generated by a variety of sources, including electrical appliances, radio transmitters, and even natural phenomena such as lightning. Isolating the ground can help minimize the effects of EMI by providing a shielded path for ground currents to flow, preventing them from radiating into the surrounding environment. By isolating the ground, one frees up a wire in the conduit, allowing for an additional hot or neutral wire to be installed. This can be particularly useful in situations where the existing conduit is already full, but additional power capacity is required. For example, if a 20-amp circuit is currently wired with two hot wires, one neutral wire, and one ground wire, isolating the ground would allow for the replacement of the ground wire with an additional hot or neutral wire, effectively increasing the circuit's power capacity by 50%. The reduction in ground currents and minimized electromagnetic interference can help extend the lifespan of electrical devices and wiring. Stray currents can cause corrosion and degradation of electrical components, leading to premature failure. By minimizing these currents, isolated ground systems can help extend the lifespan of electrical equipment and reduce the need for costly repairs or replacements. Isolated ground receptacles provide a convenient way to troubleshoot ground faults without disrupting other circuits. In a conventional grounded system, a ground fault can cause all of the circuits connected to the same ground bus to trip, making it difficult to isolate the source of the problem. With an isolated ground system, each circuit has its own dedicated ground path, allowing for individual circuits to be tested and isolated without affecting other circuits. The NEC addresses isolated grounding in section 250.96b, providing specific requirements for its implementation. This section mandates that the grounding conductor of an isolated circuit must be insulated from the equipment grounding conductors of other circuits. This insulation is crucial to prevent the flow of unwanted currents between the isolated ground system and the standard grounding system. The isolated grounding conductor must be identified by a distinctive green color with one or more yellow stripes. This color coding makes it easy to distinguish isolated ground conductors from standard equipment grounding conductors. The use of isolated ground receptacles is particularly common in sensitive electronic equipment such as computers, audio equipment, and medical devices. These devices are highly susceptible to noise and interference, and isolated grounding can significantly improve their performance and reliability. When designing an isolated ground system, it's important to carefully consider the specific needs of the application. Factors to consider include the sensitivity of the equipment being powered, the level of noise and interference present in the environment, and the applicable electrical codes and standards. The use of appropriate grounding techniques, such as star grounding, can further enhance the effectiveness of an isolated ground system. Star grounding involves connecting all ground conductors to a central grounding point, minimizing the formation of ground loops. Proper installation of an isolated ground system is critical to ensure its effectiveness. The grounding conductor must be securely connected to the equipment being powered and to the building's grounding electrode system. All connections must be clean and tight to minimize resistance and ensure a reliable ground path. Regular inspection and testing of isolated ground systems are essential to verify their continued performance. Ground resistance measurements should be taken periodically to ensure that the grounding conductors are providing a low impedance path to ground. Visual inspection should be conducted to identify any signs of damage or corrosion to the grounding conductors or connections. In addition to isolated ground systems, other grounding techniques can be used to improve the safety and reliability of electrical systems. These techniques include equipotential bonding, which involves connecting all metallic objects in an area to the same ground potential, and surge protection, which protects electronic equipment from voltage surges. By implementing a comprehensive grounding strategy, it is possible to create a safe and reliable electrical system that minimizes the risk of electric shock, fire, and equipment damage. The choice between using an isolated ground system and a conventional grounded system depends on the specific application and the level of noise and interference present in the environment. In situations where noise and interference are not a significant concern, a conventional grounded system may be adequate. However, in sensitive electronic equipment and environments where precise measurements are critical, an isolated ground system is often the preferred choice. The cost of implementing an isolated ground system is typically higher than that of a conventional grounded system. This is due to the need for specialized components such as isolated ground receptacles and insulated grounding conductors, as well as the additional labor required for installation. However, the benefits of improved safety, reduced noise and interference, and enhanced equipment performance often outweigh the additional cost. When selecting an isolated ground receptacle, it is important to choose one that is specifically designed for isolated ground applications. These receptacles have a green triangle marking on the face to indicate that they are part of an isolated ground system. The grounding contacts of an isolated ground receptacle are typically isolated from the receptacle's mounting strap, which is connected to the building's grounding system. This isolation prevents the flow of unwanted currents between the isolated ground system and the standard grounding system. When installing an isolated ground system, it is important to follow the manufacturer's instructions and the applicable electrical codes and standards. Improper installation can compromise the effectiveness of the system and may even create a safety hazard. It is recommended to consult with a qualified electrician to ensure that the isolated ground system is properly installed and meets all applicable requirements. In addition to the benefits discussed above, isolated ground systems can also provide improved protection against lightning strikes. Lightning strikes can generate high voltage surges that can damage or destroy electronic equipment. An isolated ground system can help to divert these surges away from sensitive equipment, reducing the risk of damage. The effectiveness of an isolated ground system in protecting against lightning strikes depends on the specific design of the system and the level of surge protection provided. Surge protection devices should be installed in conjunction with an isolated ground system to provide comprehensive protection against lightning strikes. The use of isolated ground systems is not limited to healthcare facilities, data centers, and recording studios. These systems can also be beneficial in a variety of other applications such as industrial control systems, telecommunications equipment, and scientific instrumentation. Any application that is sensitive to noise and interference can benefit from the use of an isolated ground system. When troubleshooting an electrical problem, it is important to first determine whether the problem is related to the grounding system. A ground fault can cause a variety of symptoms such as tripped circuit breakers, flickering lights, and electrical shocks. To troubleshoot a ground fault, it is necessary to isolate the circuit and test the grounding conductors for continuity and resistance. An isolated ground system can make it easier to troubleshoot ground faults by allowing for individual circuits to be tested and isolated without affecting other circuits. If a ground fault is suspected in an isolated ground system, the first step is to check the isolated ground receptacle for proper wiring. The grounding conductor should be securely connected to the receptacle's grounding terminal and to the building's grounding electrode system. If the wiring is correct, the next step is to test the grounding conductor for continuity and resistance. A low resistance reading indicates a good ground connection, while a high resistance reading indicates a problem with the grounding conductor or connections. In some cases, a ground fault may be caused by a faulty appliance or piece of equipment. To isolate the faulty equipment, it is necessary to disconnect it from the electrical system and test it for continuity between the hot, neutral, and ground conductors. If continuity is found between any of these conductors, the equipment is faulty and should be repaired or replaced. Proper grounding is an essential component of any electrical system. It protects people from electrical shock, minimizes the risk of fire, and improves the performance and reliability of electronic equipment. Whether to use a conventional grounded system or an isolated ground system depends on the specific application and the level of noise and interference present in the environment. By understanding the principles of grounding and the benefits of different grounding techniques, it is possible to create a safe and reliable electrical system for any application. In summary, isolating the ground on a 20-amp receptacle provides multiple benefits. Firstly, improve safety by reducing the risk of electrical shock and preventing nuisance tripping of breakers. Secondly, ensuring code compliance, particularly in healthcare settings. Thirdly, reducing noise and interference in sensitive electronic equipment. Other benefits include increased circuit capacity, improved circuit longevity, and convenience in troubleshooting ground faults. Therefore, careful consideration should be given to implementing isolated grounding systems in appropriate applications to enhance safety, reliability, and performance.